Welcome, folks. Uh, this is we are still on chapter number 4, that is the breakdown in gaseous dielectrics. In the last lecture, we learned about the streamer breakdown mechanism and also Paschen's law, which is strictly valid for uniform field, but later it was worked out also for weakly non-uniform field. There is one thing I would like to communicate about that. When we reach the Paschen's minimum, remember, when we reach the Paschen's minimum, there is a kind of a controversy. This is the Paschen's minimum, as you see here. There is a controversy whether actual breakdown occurs there or there is a pressure below atmospheric pressure, something around 25 torr, when the air acquires plasma state, and on applying the voltage at that pressure, it is not the breakdown as we see in other dielectrics or gaseous dielectrics occur. Instead, the air in the chamber, in the pressure chamber, it has to be done, acquires a plasma state. And there, the Paschen's minimum, at the so-called Paschen's minimum, the Paschen's law is not valid, because Paschen's law is valid only when breakdown occurs. So there is some confusion among people's mind, and which we have studied, and we realized when you lower the pressure something around 25 torr and slightly below, it is not actual breakdown occurs, and when you lower the pressure further, again the vacuum formed attains not the plasma state, and proper breakdown occurs. So there is a controversy about the Paschen's minimum. As we what Paschen's derived, we have learned in the last lecture once again. The many scientists, for example, Schumann, Soest, Schroeder, they derived an equation for breakdown, an analytical equation for breakdown of air in uniform field was derived. And this was also verified for weakly non-uniform field, as you will see. The equation works out to be that UB capital, UB peak, this is the UB peak as you see here, works out to be equal to 6.72 under root of PD plus 24.36 multiplied by PD in kV. And if you perform in atmospheric air, considering the pressure to be 1 atmospheric pressure, in this equation the pressure is in atmospheric pressure. So if you take 1 atmospheric pressure, the equation reduces UB peak to be equal to 6.72 root D plus 24.36 D. And in uniform field, you can also use for UB is equal to EB by D, and sorry, UB by D is equal to EB. Get it? UB by D is equal to EB. So when you divide the right hand side, both left and right hand side, it works out that EB peak, that is peak breakdown field intensity, will be equal to 24.36 plus 6.72 divided by root of d, where d is in centimeters. And this equation for increasing gap distance in uniform field has been plotted, as you can see there in this figure, and breakdown voltage characteristic of atmospheric air in uniform field, and this is very interesting characteristic. When we did define what is intrinsic strength of any gaseous dielectric, that is the breakdown strength in uniform field for a gap distance of 1 centimeter. And when you do that here, I mean, when you plot this, the for 1 centimeter here, it works out to be here, this is 10 to the power of 0, this is 1 centimeter, you get it here, 31 kV per centimeter. This is the peak value of the breakdown voltage of breakdown field intensity for 1 centimeter gap distance. Interesting is the curve on its right as well as on left. When you increase the gap distance and measure the breakdown strength, this this has been found later that this equations derived by Paschen are also valid for weakly non-uniform field. So for something like 10 centimeter and above, what you see 10 centimeter and above, you see flattened curve, and it flattens to a value of about 25 kV per centimeter. So below below 31 kV, that means above 1 centimeter gap distance, the breakdown strength reduces and it saturates, you can say in this way, for weakly when you remain within weakly non-uniform field to 25 kV per centimeter. But still more interesting is when you measure the breakdown for smaller gap distances than 1 centimeter, the breakdown strength of the air, atmospheric air, increases, and people have measured something for 0.1 millimeter gap distance for a for gap few millimeter, and it has been measured to rise to 92 kV per centimeter for a gap distance of 0.1 millimeter. But it's very difficult to perform such experiment. 0.1 millimeter, you could then convert the breakdown strength measured directly with the gap distance, because it is uniform field. U by D is equal to E in that case, and when you measure the magnitude of breakdown voltage, you can convert it for kV per centimeter, and that works out to be, as you can see, for 0.1 millimeter gap distance to the of the order of 92 kV per centimeter. So what do we conclude here? We conclude that the breakdown strength of a gaseous dielectric, even in uniform field, is not constant. It depends upon the gap distance. Obviously, when the gap distance is increased, the breakdown strength reduces. So this is what a very important conclusion we can draw here. Yeah. So when we are still in weakly non-uniform field configuration, the it has been experimentally verified and also analytically verified. The breakdown strength can be calculated or estimated with the help of a analytical knowledge or analytical formula using the Schweiger factor, eta. The breakdown mechanism in weakly non-uniform fields is similar to uniform fields. Like in uniform fields, the two characteristics in uniform field and weakly non-uniform field we have learned earlier. In the two fields, similar characteristic is that no partial breakdown activity takes place. Partial breakdown activity is a stable partial breakdown over the time. In case of both these fields, uniform and weakly non-uniform fields, as soon as the partial breakdown activity begins, the total breakdown takes place. That means no stable partial breakdown activity, so no corona activity takes place. Corona is the partial breakdown in gaseous dielectrics. So no corona takes place in uniform as well as in weakly non-uniform fields. And therefore, the corona or the partial breakdown inception voltage Ui is equal to the breakdown voltage, and which can be estimated with the help of this formula if you know the Schweiger factor eta correctly. And here you can always calculate eta if you know the dimensions of the electrode, because eta is nothing but equal to E mean by E max in the electrode configuration. And it can be seen that the gap distance d between the sphere we will, or between any two plates, we'll come to the between two spheres. It has been calculated. As it is increased, the Schweiger factor decreases. When you increase the gap distance between the two electrodes, the Schweiger factor decreases. The field becomes more non-uniform. If the measured value of UBD characteristic are known, then EB max D characteristic can be plotted. And from these curves, we will see here what I was talking about is the measurement of breakdown characteristic of atmospheric air between two spherical electrodes, as you can see it here, of radius 5 centimeter for a gap distance increasing from very small gap distance up to 8 centimeters. That means a little less than the diameter of the sphere used for this measurement. The breakdown voltage, as you can see, this is the breakdown voltage. AC peak is breakdown voltage. This has been measured to be, and when you increase the gap distance, and then the eta factor, which can be calculated for is a dimensionless factor for varying gap distance. This is the curve for eta. Eta reduces as you increase the gap distance, and then you can also estimate EB max, because eta is equal to E mean, which is U by D divided by E max, or you can say B max. That means EB max means the maximum breakdown strength, maximum electric field strength at the instant of breakdown in the configuration. EB max means the maximum field intensity in the gap at the instant of breakdown. This is not the average field intensity, this is the maximum field intensity. And the maximum field intensity will always be at the tip of the electrode, in this case the spheres. And EB max is plotted here, as you can see it here. EB max is higher than the breakdown strength, you can say, the breakdown field intensity, you can say. So EB max, this is a very, very interesting characteristic for weakly non-uniform field. What we conclude from this figure, for this particular electrode configuration, it is limited to a gap distance nearly equal to the radius of the sphere. That means the field, the configuration which remains under the weakly non-uniform field configuration, that is limited up to a gap distance nearly equal to the radius of the sphere. We will see it here. What is the difference? This is the radius of the sphere is 5 centimeter. We can see here the breakdown characteristic is almost like a straight line, and it deviates above a gap distance of 5 centimeters, that is the radius of the sphere. So you can say the field remains to be in under weakly non-uniform configuration till up to a gap distance equal to the radius of the sphere. This is a very important conclusion. Based on this conclusion, in the earlier days, when the measurement of voltage techniques were not very developed, people used to have two spheres for measurement of the voltage, and the only way to estimate the voltage applied was when a breakdown was created, and the breakdown characteristic, as you see, is linearly proportional. It is a straight line up to this gap distance. So this was used very widely for the measurement of high voltages of all the types. There are tables available. We'll come to it little later. Okay. Yeah. Now let's talk about the breakdown voltage characteristic of SF6 gas and its mixtures in weakly non-uniform field. Because we have left behind the uniform field, as I have been mentioning, uniform field does not exist in practice. It is only an ideal field configuration. The field which actually exists in practice and it is adopted in practice is the weakly non-uniform field, where when the eta factor is less than 1. Eta factor is, for uniform field, eta factor is 1. So in the apparatuses developed for compressed gas, for air as dielectric, or for SF6 gas as dielectric, the weakly non-uniform field configuration is developed because you can imagine, as in uniform field, also in weakly non-uniform field, no partial breakdown activity takes place. Even in the gas, we do not want any partial breakdown activity because it will degenerate the gas and the insulating qualities, insulating properties of the gas. So when we adopted SF6 gas as an insulant, the efforts have been made to remain within the weakly non-uniform field configuration. The insulation system with atmospheric air acquire very large dimension, and the electric field in these systems is mostly extremely non-uniform. What am I talking about here? Is as you see in overhead transmission lines. The prevalent field there is not uniform, is not weakly non-uniform, but only extremely non-uniform field. So above a certain voltage application, the partial breakdown or corona activity would take place there. But the scenario in SF6 gas, which is in enclosed chamber, is different. In atmospheric air, even if the quality of atmospheric air is disturbed or polluted because ozone is produced due to corona activity, we do tolerate it to a great extent. But it cannot be tolerated in case of the enclosed chamber gas, that is SF6 gas. The compressed SF6 gas, found to be a suitable alternative to air and also nitrogen. It is widely used in power system, in power apparatus since 1960. The work started before that, but after 1960, its application, this SF6 gas made its breakthrough initially for high voltage circuit breakers. But very soon, technologies for complete metal clad substation with SF6 gas was developed. As you see in this picture, it is nothing but a metal clad substation. This substation is developed in Japan by Toshiba for 1100 kV, one of the highest voltage still existing on our earth. And the same substation, if it was built in open air or atmospheric air, it would have occupied 10 times more space. Here, as you see it, all bus bar and the whole system here, all this here, what you see is in metal clad. That means the voltage is carried inside these you can say coaxial cylindrical form of containers, and the voltage outside on these metal clad is ground potential. Inside 1100 kV, unbelievable for some. The SF6 gas made its breakthrough initially for high voltage circuit breakers, as I said, but later it has taken over for gas insulated system. People gave different name. If you abbreviate circuit breaker, people also said gas insulated switchgear. Then the better terminologies would be gas insulated substations or gas insulated system, developed. And this could be developed because of the properties of SF6 gas is very suitable for electrical insulation, for arc quenching, for under pressure carrying the thermal energy away. For so many purposes, SF6 gas was found to be very suitable, and its application increased very rapidly. Yeah, this is a sectional view of the SF6 gas substation, what I showed you in the last slide. And then you also see here the 1100 kV SF6 gas. This is the 1100 kV SF6 gas substation GIS. The figure B is the sectional view. A was the one in the last slide, B is the sectional view, and this was developed by Toshiba Japan. I'm thankful to them for their picture here. And in the picture C and D, you see a 1200 kV SF6 gas insulated circuit breaker. In C, this is the circuit breaker SF6 gas at 1200 kV rated voltage, and by Siemens. This is by Siemens 1200 kV. Imagine, of course, the bushings have to be very big. As you can see, the bushings for 1200 kV have to be very big. But the circuit breaker chamber comparatively is very small. So this is how the SF6 gas has found its application in power apparatus. Yeah. What happened? What is SF6 gas? Is fluorization of sulfur. That means it is not a natural gas. It has been produced by fluorization of sulfur atom. And in order to bring down the cost, because it has been commercially produced, this SF6 gas, so it's a very costly gas. And when the application of SF6 gas increased very widely, the demand for the volume of SF6 gas increased tremendously all over the world. So a very prime aim of all the engineers is to bring down the cost of the equipment and yet produce the high quality equipment. So it was thought to try the mixtures of SF6 gas, mixtures with other gases which are having suitable properties. For example, mixture of SF6 gas with nitrogen. You know that nitrogen is an inert gas. Mixture of SF6 gas with CO2, carbon dioxide, helium. They were all tried to be studied, and of course later it has found wide scale application and brought down the need of SF6 gas, demand for SF6 gas to a great extent. It has brought down the cost of the equipment also. So as you can see in these three curves here, the first one is the SF6 gas, mixture of SF6 gas in percentage wise with nitrogen. On the right side here is purely SF6 gas, and on the left side here is the purely nitrogen gas, and the mixture is increased. SF6 content by volume, you can say, has been increased, and as you can see, the measurement of breakdown strength has been done in uniform field, as we have been talking. That is the best way to do it at varying pressure. This is 1 atmospheric pressure, this is about 2 atmospheric pressure, and this is 2.5 atmospheric pressure, as you can see. When you see these curves, on the right side is pure SF6 gas, but by achieving 50% mixture of the SF6 gas and nitrogen, almost 90% of the breakdown strength is obtained as of pure SF6 gas. Obviously, the breakdown strength of pure nitrogen is much lower, but 90% of the pure breakdown strength of pure SF6 gas is achievable by using only 50% SF6 gas and 50% of nitrogen. And the same thing has been also obtained here. People have measured here the nitrogen and helium. So the full curve is that of nitrogen and SF6 gas, and the lower one is with helium. Again, this has been measured not in a uniform field electrode system, but for weakly non-uniform electrode system. Then the average negative switching impulse breakdown voltage. This is again here in the middle curve, middle figure, you see the breakdown voltage of DC. This was AC, this is DC, and this is for the peak value of the switching impulse voltage. SI is the switching impulse voltage, and this has been measured for coaxial cylindrical system. As you can see it here, this is for a coaxial cylindrical system, and average negative switching impulse voltage characteristic for a coaxial cylindrical electrode geometry with SF6 gas and nitrogen. And in all these curves, as we see it here, 50% when you achieve the breakdown strength, and this is at 1 atmospheric, almost 90% of the breakdown strength is achieved. So the mixture of nitrogen and SF6 gas 50-50 has proved to be very suitable, and I believe it is being used very widely. All these measurements you can see have been done. This is up to 0.3 megapascal, that is 3 atmospheric pressure. This has been done up to 6 atmospheric pressure. You can say 0.662 megapascal, and this is at 1 atmospheric pressure. So you learned something about the use of SF6 gas in power systems. And an interesting thing to be learned at this stage is, an interesting thing to be learned at this stage is, what is that value of eta where the field configuration changes over from uniform to weakly weakly non-uniform. Sorry, what is that value of eta when the field configuration changes over from weakly non-uniform field to extremely non-uniform field. Because when you increase the gap distance between any two electrodes, if you have for weakly non-uniform field configuration, when you increase the gap distance, beyond a certain gap distance, the field will be rendered to be extremely non-uniform. Extremely non-uniform field means when the breakdown will be preceded by partial breakdown activity. That means when you maintain a certain voltage, there will be continuous corona activity, partial breakdown activity in the field. Whereas in weakly non-uniform field, as I mentioned, there is no continuous partial breakdown activity. As soon as the partial breakdown begins, the total or complete or global breakdown is achieved. So the value of eta, I'll just read it out. The value of eta at which the transition from weakly non-uniform to extremely non-uniform field configuration takes place, and this value of eta is termed as eta limit. We'll devote a few minutes to learn about eta limit. The exact value of eta limit in gaseous dielectrics depend not only upon the field, upon the field non-uniformity, but also upon the gas pressure. It will be different at atmospheric pressure, and it will be different when you increase the atmospheric pressure. You know, I think I have mentioned, you may be knowing that it is advisable to use the aseptic gas at higher atmospheric pressure because you achieve better insulating properties. And it also depends upon this eta limit. The value of eta limit depends upon the polarity of the voltage, since it is related with the inception of partial breakdown. The partial breakdown inception voltage depends also upon the polarity of the voltage applied. The question of polarity of the voltage does come in DC. It does come in lightning impulse or switching impulse also. In AC, it is alternating. So this characteristic, this is a schematic. We have measured also this characteristic. But let's try to understand the from the schematic, how is the eta limit defined to be. Between the peak value applied between the electrodes and the gap distance is being changed, and when you measure between a sphere and a plane. So when the gap distance is very small between a plane and a sphere, the field is weakly non-uniform. As you increase the voltage at some gap distance, let's say here at this gap distance, the field pattern or field classification changes, and the full curve this is the breakdown curve, and above eta limit, not above, when you increase the gap distance, in fact the eta becomes smaller. For a value eta less than eta limit, for a value, eta less than eta limit, the partial breakdown activity would begin first, that is shown here with dotted curve. You measure the partial breakdown activity and then you increase the voltage, full complete breakdown occurs here also. Between the voltage when the partial breakdown activity begins and the full breakdown or complete breakdown is achieved, there is stable partial breakdown activity. Because the gap distance here is sufficient, as we learned earlier, we'll talk about it. Because the gap distance between the electrodes is sufficient, what kind of partial breakdown activity would occur? The partial breakdown activity would take place with above critical amplification of the avalanches, and that is known as streamer. Stable streamer would be produced. Because if the gap distance was very small, as in the case of pure uniform field, the critical amplification of avalanche would not have been able to take place. But when the gap distance is sufficient, a critical amplification of avalanche would take place, and there will be a streamer corona, what we call it to be. Activity takes place in the region of this curve, as you see, after the inception of breakdown, after the inception of partial breakdown till up to the complete breakdown. When we plot a tangent here to the initial of this curve, this tangent would work out to be for, say, DC 25 kV per centimeter. The field intensity is 25 kV per centimeter. And for DC positive polarity. And this would reduce when you increase the gap distance, and then this kind of a curve, as you can, this is the breakdown voltage curve, is measured. This breakdown voltage would reduce considerably. To what extent, we learn in the next graph. In this region here, you can, this is A region, the eta value, actual eta value in the electrode configuration is more than eta limit. Whereas in the region B, the eta value is less than eta limit. And this is the value of eta in between, as you can see. So I hope you have learned, you understood what I'm trying to convey here. And in A region here, this equation is valid because in uniform field and weakly non-uniform field, Ui, the inception voltage of partial breakdown, is equal to the breakdown voltage, and it can be achieved by this equation. And in B region, you can what is the maximum breakdown, what is the maximum electric field intensity in the electrode system, that can be estimated with this equation. Ui, the means partial breakdown inception voltage, will be equal to EB max into D into eta. That means UB here is a function of eta, but UB in extremely non-uniform field cannot be estimated with the Schweiger factor eta, but the inception voltage of partial breakdown can be estimated to a great extent in extremely non-uniform field configuration. Here, in extremely non-uniform field configuration, the breakdown voltage is dependent upon the potential gradient across the streamer channel. That is, for positive polarity DC voltage, the potential gradient, as you can see, of this curve, potential gradient of this curve works out to be 4.5 kV per centimeter. If the streamer is extending up to the opposite electrode, then 4.5 kV per centimeter multiplied by the gap distance will give you the breakdown voltage. And that is what is written here. UB is equal to ES, that is the potential gradient across the streamer partial breakdown activity multiplied the extent it is extending. If it is extending over the complete gap distance D, then the breakdown voltage can be estimated in this way. Give a thought to it. I hope you will understand. Yeah, the same things are described here. A breakdown when eta is greater or equal to eta limit. This is the region A, as I mentioned. This equation gives you the breakdown voltage, and the breakdown voltage for the region B is given by the equation, that is the extent to which the streamer breakdown mechanism has the streamer breakdown channels have extended to. And in this case, the complete breakdown will occur only when the streamer breakdown, that is partial breakdown channels, extend up to the opposite electrode, that is cover the distance of D. And yeah, when the value of eta limit, numerical value of eta limit can be estimated with these equations. For atmospheric air can be estimated. That means when by the two cases the breakdown voltages are equal in the uniform field, in the weakly non-uniform field, and in extremely non-uniform field when these are equal. This gives a value of eta limit to the order of 0.2. That means if the eta factor is maintained to be equal to 0.2 or more, the field will be uniform. And anywhere in the electrode configuration in an apparatus, if the eta value goes down, that means less than 0.2, the extremely non-uniform field configuration would begin. And this was plotted we talked so far about DC voltage application. We plotted in our lab an AC power frequency voltage taking the two spheres of 9.92 millimeter diameter for increasing gap distance D up to 70 millimeter. This is a long distance compared to the diameter of the spheres. So we initially we have the weakly non-uniform field, and then it increases to the extremely non-uniform. This is exactly, as you can see, this characteristic here plotted is very much like what we saw in this schematic. This was a schematic, and this was the measured characteristic. Exactly same pattern we get for weakly non-uniform field, the tangent shows 25 kV per centimeter. And for AC power frequency, this has been measured with AC power frequency. As we must know, when you apply AC power frequency alternating voltage, the breakdown would always occur at the peak of the alternating voltage. So 7 kV per centimeter is the peak of the alternating voltage, not RMS. AC peak it is, mind it. UV is AC peak, as you hear. AC peak voltage has been plotted here. Yeah, and again, in case of uh, uh, in case of AC breakdown voltage, this value 4.57 has been estimated with the tangent to the curve here, the breakdown voltage curve. And when the streamer channels extend to the opposite electrode, the potential gradient in the field configuration is of the order of 4.57 kV per centimeter. That is the estimated potential gradient across streamer, you can say. So this is a very good conclusion what we could make in our laboratory long time back, and that is how the the streamer is fully defined to be. So we make a break today. For today here we will uh, meet after we'll meet tomorrow with and continue with the breakdown voltage in more about in extremely non-uniform field configuration in air and also in SF6 gas. Okay, see you tomorrow.